Hi everyone, welcome back to the On Track Whiteboard video series. I'm Ben Jordan, and today I'm going to be carrying on in our RF and PCB, or RF and microwave PCB design series. Today we're doing part 3 in the series, which is, and let's write this up here, introduction, because it really is just an introduction to stubs. Stubs are something that you're going to encounter in every RF design at the board level, or even using transmission lines made of coax, going to an antenna or an amplifier or something like that. You almost always will encounter stubs somewhere, and these are curious bits of this is where the curiosity is piqued by seeing strange shapes on the PCB and wondering what the heck is all this for and what does it do. So to get started, let's just consider the most basic transmission line stubs you're going to encounter, and we'll take a look at a couple of examples where they might be used. So here I have a drawing with characteristic system impedance Z0 or Z0 if you're from Australia like me, driven by some kind of source. We don't know how far back that is, it doesn't matter. The transmission line gets it to that point intact. And a stub is where we encounter a segment of transmission line like that is either terminated, now it could be terminated resistively or capacitively, but normally, almost always, it's going to be in an open circuit or a short circuit to ground, or maybe a power supply. So we'll look at those cases, and then the transmission line carries on to the load impedance. So what does a stub do? A stub is a piece of copper that's going to resonate at a particular frequency. And let's have a quick look at some of the characteristics of stubs. I've got my notes here. So from an earlier, from probably episode 1 or 2 of this series, where I mentioned some of the characteristics of transmission lines, and we talk about its characteristic impedance. There's other parameters we talked about, the velocity of propagation, VP, for example. So we have this thing VP, or V sub P, and that's how long does it take for an electromagnetic wave or a signal to travel down the line for a given distance. And we have from that and from the frequency of interest, so we have omega, and omega, as all engineers would have seen or know, is 2 pi f. So this is the angular frequency of interest in radians. So if you look at a different frequency, you get a different omega. And there's this propagation constant, gamma, which is typically alpha plus J beta. We looked at that in an earlier video. So what does this mean? This is our losses, and we talked about losses last time. And if you neglect losses, we have this J beta, which has this beta thing. So what is beta? Beta is our omega over the velocity. And this makes sense. So what we're saying is we have this parameter beta that represents at the frequency we're interested in or talking about or doing math around, for a given velocity. This is the angle it takes for a wave, or for a given length of line. We want to look at, for a given line length, how much of a wave angle is that? And we talked also last time about, this magical distance that we're interested in, which is wavelength, and then 1/4 of that. So these stubs in practical transmission lines will almost always universally be 1/4 of a wavelength, almost always 1/4 of a wavelength long. Now why is that? I'll tell you why. It's because when you have a segment of transmission line, and this gets into reflections, if you have a segment of transmission line and it's terminated in an open circuit, so there's a ZL of infinity, right? 100% of the energy of the wave traveling down that line must be reflected back. Okay, so that's fine. And because this is an open circuit, the voltage at this end can be anything. But the current must be zero. So the current is held at zero here, and the voltage, the reflected voltage, when a wave reaches here, it is doubled. It's effectively doubled. So you have this standing wave that occurs. We'll talk about that more in a moment, where this chunk of transmission line is reflecting all of the wave energy back, and that at a quarter wavelength back from that open circuit, the voltage stays at zero because we end up with a standing wave that goes up and down as the forward wave and the incident wave add up and cancel out, or add up and double but create a standing wave. So what we have is this concept where you have a transmission line. And so let's draw it again over here. If we have a transmission line of Z0 going into some kind of load, which may be another transmission line segment of ZL, then we have this thing that's called the reflection coefficient. I think that's a capital gamma, but forgive me if my Greek is rusty. And that is this ratio that's ZL minus Z0 over ZL plus Z0. And so this thing represents how much of the wave is reflected back when you have an impedance mismatch. If ZL is 0, then you have minus ZO over ZO, and that means all the energy is reflected back because you have a reflection coefficient of -1. If ZL is a short circuit, sorry, that's if ZL is a short circuit. You have a coefficient of -1 means everything's reflected back, but it's inverted. So the reflected wave is negative. And you see that in a time domain reflectometer. When you put a pulse down a shorted line, you see the pulse can travel down the line, and then when it reflects, it comes back negative, and you can actually see that on the display of the TDR and see how long that line is based on the time intervals between when these pulses, positive going pulse and negative going pulse, occurs where you're measuring it. Okay, so let's grab the eraser there real quick. Got to make some room. So what happens in the case where ZL is an open circuit? Well, this is infinity, and we can't really, an open circuit is infinite impedance, so it's infinitely high. So we can't really do the math on that because you can't divide by infinity, but this essentially approaches 1. Oh, 0, sorry, my mistake. And so with an open circuit, all the energy is also reflected back, but it is not inverted, as we discussed over here. So with an open circuit at a quarter wavelength back from the open end, it looks like a dead short because the voltage is always 0. Okay, so a quarter wave back from the open, we have a null, and the voltage is fixed at 0. So a quarter wavelength long piece of open circuited transmission line, which is called a stub, appears to be a dead short, but only at this frequency where that happens to be a quarter wavelength long, depending on all our other transmission line calculations, which we did in the previous episodes. Okay, so there's another case. Stubs can be terminated in a short circuit. And let's say if there's a quarter wavelength stub that's shorted to ground. Now remember, it's ground to AC, so it could actually be a VCC supply rail, and there's a very practical use for this kind of stub. The same thing happens, only here the current is 0 instead of the voltage, and at the shorted end the voltage must always be 0 because it's terminated at ground, assuming your ground is very good. And of course, you know, there's ground currents and things like that too. So you want to have a very solid ground plane and via stitching and all those things. The reason RF engineers want those things on a PCB is to make sure your ground is as ground as possible. Okay, so if that's fixed at ground for a quarter wave stub that's terminated to a short, what do we have? Let's redraw that little waveform there. All the energy is reflected, but reflected in reverse. It's negative. And the voltage of the standing wave is fixed at 0. And so then we have at a quarter wave a peak. And so a quarter wavelength stub shorted at one end appears like an open circuit. And there's something else that's interesting about these stubs. A short-circuited stub for any wavelength less than half generally appears like an inductor. It's very inductive, but it has, of course, there's capacitance to your ground plane on that as well. So it's going to have resonances. And the same thing with an open circuit stub. Anything less than half a wavelength long, it's mostly capacitive. And so we can use these as tuning elements and filtering elements. And these stubs therefore form the basis of almost all the other structures you see in microwave PCB designs. So let's see, what are some of the other things we can learn about stubs? These are just the basic stubs that are a section of uniform ZO. They're the same diameter, same width as our regular strip lines or microstrips. So what happens? As we get close to that resonant frequency of 1/4 wavelength, if we're either side of that, these show themselves to be very narrow band structures. So if I have at the frequency of interest, the open circuited quarter wave stub appears to be a short circuit. So if I were to let's draw a little graph here. We have amplitude versus frequency. It's not a very good F. Okay. And there's DC down here. Then we're sending a signal down through here to some load. Our transmitted power to the load, right? And maybe we'll come back to this in a future episode, which is called S21. It's our transmitted power to the load that gets through this circuit and gets to the load. Is going to be at 0 dB, right? And at the frequency where this is a quarter wavelength, that an ideal stub will bring that down to 0 because it appears like a short circuit at that frequency. And then as the frequency goes higher, it goes back up again as this becomes less and less significant. Remember in the first video when I said, and this is true, if the wavelength of the frequency of interest is, if the feature sizes on the board are some reasonably long enough to become a significant fraction of a wavelength, then you have to treat them like these kinds of elements. And if your features on the board are much smaller than a 16th or a 20th of one wavelength, then it's kind of like, what's a good analogy? It's like saying, you know, the trees that you look at on a hill, if they're just shrubs, they just look like part of the hill. But if you look at a giant, tall king or queen palm tree or whatever they're called, and they stand right up straight, then they're pretty significant compared to the size of the hill. So you notice them, you see them, and it's no different here. You know, it's a pretty pathetic analog, I know, but it's the same kind of idea. And so here, when this is some multiple of quarter wavelengths, it's going to resonate and form that short circuit behavior. So what actually happens as you keep going up in frequency, you start to develop these repeating notches as you go higher and higher in frequency. And the depth of the notches usually in a practical circuit will decrease. But why is this? It's because you're getting closer to some frequency where this is actually a multiple of quarter wavelengths at those frequencies, or some reasonable fraction thereof. And so just be aware of that, because you know you'll be designing a circuit for one frequency and you might discover that it's taking effects at other frequencies and letting things through that you didn't think it would let through, which is more often the problem, you know, transmitting something you don't want to transmit. Okay, and the same thing happens with quarter wave stubs that are terminated in a short, except that those are the opposite. So here at DC, it's going to be just a dead short. But basically, so at DC we're starting at 0. Here's our amplitude. At DC we're at 0, because that's a dead short at DC, right? And then at some frequency it behaves at our frequency of interest as an open circuit. So it's got the opposite shape. And then the same thing happens again. It repeats at those multiples of the quarter wavelength. And so this forms the open circuit stub in its crudest form is a band reject or notch filter. The short circuited stub in its crudest form is a band pass filter, but they're very narrow band devices. So the range of frequencies that get passed here is only within, you know, maximum 3% of the center frequency, typically. So they're very crude, but it works. It does the job. And what I might do is insert a little video here showing some filters I've actually made like this using the mill, and I'll show their frequency response with the VNA, the desktop VNA, so you can see that it's true and it really works. So what's an example? How would you go about figuring out what size you need these to be? Oh, and by the way, normally for a microwave circuit, we are working with a fairly narrow band usually of frequencies. We've got our carrier and then we modulate the carrier, so we have some bandwidth needed on either side. But it's very important to build and test these so that you're as close as possible to your frequency of interest, because the slightest thing can shift the characteristics of this circuit and move it to some other frequency that you don't want it operating at. And this happens with antennas as well. So we'll talk about that more down the road, but let's walk through an example how you might calculate this kind of thing. Okay, so let's say, since I'm using a purple pen, I'm just going to give a quick shout out to Lane and my buddies at Osh Park, who have often helped me out with boards. So let's say I'm using Osh Park and I'm doing a 4-layer design, and you really want to do a 4-layer design with RF and microwave, because otherwise your feature sizes get much too big and your losses go through the roof from your dielectric losses, because on a 2-layer board you have a much thicker dielectric. So to get the same impedance you need much larger geometries, you need more area, but you're going to get more dielectric loss. So go at least for a 4-layer board where you have a very thin dielectric between the top layer and the next layer down for your ground plane. Okay, so that's what I'm doing, and I'm going to use their 4-layer process. 4-layer, and this is what it's going to look like. I've got I'm going to open the solder mask over my traces. Now they use ENIG, which does affect the performance a little bit, but just for example's sake I'm going to keep it simple. So there's my copper trace with the purple solder mask around it. Then I have a layer of dielectric, which is FR408. Here's my FR408. Sorry for my shoulders covering the diagram here. FR408. And then I have another layer. Let's put that lid on. Then I have another layer of copper underneath, which is mid layer 1, and that's it's layer 2 according to IPC standards. So layer 1's the top, layer 2 is down here, and that's solid ground. So that's my reference plane. Let's grab the black here. So what are our dimensions? We have 1 ounce copper on the top. So the thickness of that copper is 35 what is it? They say on their website, they do 35.6 micrometers. That's the thickness of my top layer, copper. Okay, then FR408, this is not drawn to scale, obviously, is going to be 170.2 micrometers. And the next layer down is ground plane, and that is ½ ounce copper, so that's 17.8 micrometers. Okay, and the FR408's epsilon sub r is they list it as 3.69 at 1 gigahertz. So if they've measured it at 1 gigahertz, it's probably not going to change too much up to about 3 gigahertz. So I'm happy with using that, and I plug that into my impedance calculator. We all have a good impedance calculator now. Uses a static field solver, but there's many tools out there you can use for free to verify your results. So I want to create a board here that operates at 2.4 gigahertz. Typical Wi-Fi or Bluetooth or whatever is usually around this. And my system impedance, Z0, Z0 is 50 ohms. Center frequency, 2.4. And therefore, to get 50 ohms, what we end up with, this pen's dying, so I'll just get a different one. We end up with, here's the trace width, W. Okay. And for that thickness, that dielectric, the trace width for a system impedance of 50 ohms is going to be 3483 roughly millimeters. So I'm going to plug that into my design rules. Of course, if you're using Altium Designer, you just tell it the impedance and it automatically plugs that into design rules, so it's a bit easier. But what I really want to know is what's a quarter wavelength? And so plugging that in as well, I get a 90-degree angle yields a length of 19.0614, and I'm using lots of decimal places because you want to be accurate with this kind of thing. Again, you don't want your frequencies of stubs and things to drift too far from center. You want to be within a few percent if you can do it. So that's a quarter wavelength, 19.0614 millimeters. And I'm going to be using that to create regions or polygons of that specific length, which I can then copy and paste or put them into a library and place them as parts. And that gives me the ability to start doing interesting things like making bandpass filters. So I have another example of that right here. And that is where we have this kind of structure. So we have our source impedance comes in. We have our input, and then I'm going to have some transmission line segment that's going to be a quarter wavelength long. And then that's going to join to a short circuit stub, a quarter wavelength long, but a slightly different impedance because we can vary things, and not to go into all the detail of why we're doing that right now, but I've got a few short circuit stubs, all a quarter wavelength long, separated by series transmission line segments, also all a quarter wavelength long. And by cascading them like this, I'm able to create, and down here at the end is the final section, and then that goes off to my load. So that's the output. And all of this together, this, 4 series sections and 3 parallel stubs shorted to ground, which each one of these on its own looks like a notch, remember, but we're spacing these out and we're adjusting their widths to change their impedances to broaden to broaden the bandwidth. And so what this eventually leads to is, at DC, it's all a short circuit. So we start there, and then if we look at the frequency response, I'm kind of running out of room here, we end up with this kind of thing. There's a bit of passband ripple, but this gives me a nice wideband bandpass filter. And so this might be a really good useful circuit to come into an analog front end. Now obviously we're dealing with microstrips. So if you have a piece of copper and you have plane under it, you've got capacitance to the plane. Okay, and that's what causes this to short really at a given frequency. It becomes a short because of that capacitance. So we can increase the capacitance if we want to broaden the range of frequencies at which it's a short circuit. How do we do that? We make it bigger. So you can have a transmission line and you can have a stub, and there's a couple of things you can do. You could make part of that stub just a bigger chunk of copper, and you'll see that in some circuits where they need capacitors for a filter. You'll see rectangles, but all sorts of weird radiation modes can happen with rectangles, and we'll talk about that in a couple of episodes away when we discuss antennas, but this could become an antenna unintentionally. So I personally don't like doing things that way. A similar approach that's a bit more common, and you would have seen this probably if you've ever looked at an RF board, is to put a radial stub. And this is still has a radius of typically a wavelength on 4. It may be less, but this is used to broaden the bandwidth. So instead of having a very narrow notch, doing this one, we have a broader notch like this kind of shape. And here's a quick video I'm going to interject here as well, showing a milled radial stub I did on the mill. And this is it on a VNA, and we can see here's the regular quarter wave stub, and now here is the radial stub, and you can see the bandwidth difference. There's no exact science or closed formula, unfortunately, for radial stubs. Almost always they're designed by intuition, and they can be modeled in software, but they require some numerical modeling techniques where each stub is divided up into tiny short transmission line segments of different widths, and then those are modeled together as if they're all in series. But most tools out there and simulators know how to do that, so that makes it much easier for us, and we can still get a good starting point before we cut metal. Just one thing I'll leave you with, and this is the cliffhanger for the next episode. Stubs lead to all sorts of other useful shapes. But there's two different kinds of transmission lines that we discussed in other videos. There's a single microstrip or strip line, but there's also a coupled line. And in high-speed digital, we call it a differential pair. That's where we run two traces at a fixed spacing side by side, and there's different reasons for doing that. Almost always in a digital design, it doesn't matter that they're coupled or not. It matters that they're the same length, because it's more about length tuning. But in an RF design, the coupling matters greatly. That's the situation where it does matter. And so we can have transmission line segments which are coupled by a very specific amount, and then those coupled line segments can also form things like resonators. And so you might have a single transmission line coming in from the source, and then have, instead of having a stub like this, you may have a piece of copper next to it that's very, very close. And there's magnetic field coupling around them and capacitive coupling between them. And usually, not always, but usually, the length at which they're coupled is a quarter wavelength. Here's that number, quarter wavelength, showing up again. And this copper then resonates because it's coupled with this one. Energy's transferred from this one to this one. But we'll talk about that in more detail with an actual worked through example in the next video. So stay tuned for episode 4, where we're going to talk about coupling and what you can do with couplers. I hope you've enjoyed this. My name's Ben Jordan. This is the On Track Whiteboard video series. Please, if you like this, give us a thumbs up, share it, subscribe so that when I post the next episode, you'll get a notification that it's ready to go, or it'll appear in your YouTube page. And if you want to see anything specific, or if you felt like you have questions that you want us to answer in more depth in this series, please comment below and let us know. And we'll do what we can to demystify RF and microwave PCB design.